Very good.
看到了。
好，没问题。Is everything okay? Looks good. To invite Professor James Liu from Taiwan, National Sun Yat-sen University, come here to talk about the submarine canyon, the river, the mountains, river, and submarine canyon system. And in this Source to Think talk series, we have already a couple canyon system talks. And like Pete Tolling talk about the Congo River, talk a little bit of the Ganges system. Charlie Paul talk about Monterey Bay, and Buri talk about the Nile River, little bit of canyon. And Anna Bennett talk about the Biobio River in the South America. And canyon definitely is a very, very important, very channel conduit transport sediment all the way from the river continent to the deep sea. So before I introduce James, and this coming Friday, same time, and 9 a.m. U.S. East Coast, and the 9 p.m. in Beijing. And I'm sorry, this week and next week, 2 weeks before the March 28th, the European time is 1 p.m. London, and Paris is 2 p.m. So after March 28th, the London will be 2 p.m. Paris with 3 p.m. They're a little bit confused during the summer sailing time, the difference between Europe and the US. I don't know why they put the same weekend. It's just crazy. But anyway, so Sarah will from Chicago School of Arts Institute. She graduated from MIT Woods Hole, chemical oceanographer, and she will talk about Amazon POC, particular organic carbon, and the source and the fit in the field, lab, and classroom. That should be a very interesting talk this coming Friday. Mark your calendar. So James is the distinguished professor, as I mentioned, National Sun Yat-sen University, and he got his PhD in Stony Brook, and postdoc Woods Hole, and also in Florida, the Harbor Branch Oceanography Institute. And his research interest is coastal geology, coastal estuary sediment dynamic, coastal change, submarine canyon oceanography, marine hyperpycnal flow, and sedimentation. And he got a reward in the Outstanding Research Award. And also, he's the leader of the program called FIT, the FIT of terrestrial, non-terrestrial sediment in the high yield particle export river system, is also a Taiwan Strait Source to Think study. So I think James, now you can share your screen and put a presentation mode.
Okay, thank you, Paul. And let's get started. There are 54 published papers directly about the Gaoping River and submarine canyon system, and I co-authored 34 of them. There are a lot of interesting subjects to talk about, but for today's talk, I chose to focus on the close coupling between the physical processes and sediment records in this system for the diverse background of the Source to Think community. Now, okay, I'll start out the Taiwan's fate. This is not the fate that politicians talk about. Taiwan is located on the collision boundary between the Philippine Sea Plate and Eurasia Plate. The collision created a very rugged terrain that there are over 200 mountain peaks in Taiwan that are above 3,000 meters above sea level. And as a result, the rivers are very short and with a steep gradient. And the collision makes Taiwan prone to earthquakes, deep and shallow, especially at where the plates subduct. You can see the blue dots are a higher magnitude. So the earthquakes shake up the source area in high mountains and make the making the mountain areas, source areas, prone to erosion and hillside mountain slide. And then Taiwan is located in the monsoon climate. The monsoon rains and the plum rain system, plus frequent visits of typhoon that created torrential rain that wash out the sediment that has already been shaken up by earthquakes, flowing down steep rivers, making all the three factors combined, making Taiwan produce extremely high sediment discharge by rivers. And Taiwan contributes disproportionately large amount of sediment to the ocean. So this caused Taiwan an ideal natural laboratory to study source and sink because of strong terrestrial signals and powerful physical drivers. So that's why it's an ideal place to study source and sink. Now, Paul, in the introduction, I mentioned that I'm leader of the Fate program, which is sponsored by the Taiwan Ministry of Science and Technology. We've been doing that for over a decade. Since 2012, a few colleagues in mainland China and the Fates group formed an ad hoc group called Taiwan Strait Source to Sink Study. So together, we use cross-disciplinary approach to study source to sink processes and records that transcend space and time. We have studied this many river sea dispersal systems in our neighborhood. And today's focus is on the Gaoping Submarine Canyon. And to start out with a bigger picture, I borrowed this figure from JP and Chuck's paper that focuses on the 5 types of river dispersal systems. We can actually assign each of the river sea dispersal system in our neighborhood to these 5 types. And today, we're talking about the canyon capture type. Okay, the Gaoping River and Submarine Canyon system consists of 2 major geographic units, a small mountainous watershed, that's the Gaoping River, and the Gaoping Submarine Canyon, whose head is just 1 kilometer outside of the Gaoping River mouth. And the canyon meanders southwest and eastward for 240 kilometers and eventually merges into Manila Trench. This is a digital terrain map of the watershed of the Gaoping River. The river has 3 main tributaries, the Lao Nong River, the Qishan River, and Ailiao River. The 3 rivers come together near the district of Meinong of the Gaoping City. And from that point on, the river is called the Gaoping River. If we plot the elevation along the talweg of the main Gaoping River stream, and this is what we get. You can see that this is a typical mountainous river, very steep slope. And these are some attributes of the Gaoping River watershed. And the source area is located at 3,500 meters above sea level, near the highest peak in Taiwan, Jade Mountain. And the mean slopes is 1 to 150. The annual suspended sediment load is about 49 metric tons. Now this varies year by year. The sediment yield is 15,000 metric ton per square meter per year. And just for comparison, Mississippi's sediment yield is 74. So the Gaoping River is 3 orders of magnitude larger than that of Mississippi. This river also has high rate of physical weathering and the chemical weathering, all above world average. So this is a extraordinary watershed, a small mountainous river system. Now, switching to submarine canyons, there are over 5,800 submarine canyons in the world. They are very important features on the seafloor. According to Harris and Whiteway, there are 3 types of canyons, one of which is inside the shelf and connect to rivers. In other words, river-fed canyons. And they only comprise 2.8% of all the submarine canyons. And Gaoping Submarine Canyon is one of them. So that's unusual, extraordinary. Now, Pete Tolling did a lineup of major submarine canyons in terms of duration and the magnitude of measured turbidity currents. And you can see that the Gaoping Canyon is right up there with other world canyons. And because of the monsoon climate, Gaoping River's hydrology displays very distinct dry and wet seasons. And you can see that usually there is a 3 orders of magnitude in the discharge and suspended sediment content between the dry and the wet seasons. The red dots are actually typhoon warning days issued by the Central Weather Bureau. So you see that extreme values occur mostly during typhoons or episodic weather events. In this talk, I will feature 3 typhoons, Kalmegi, Morakot, and Fenapi, and their tracks are plotted here. Gaoping Submarine Canyon was formed by the tectonic process of collision between the Taiwan origin and the Chinese continent. And the same process also created an echelon of submarine canyons in this area. The canyon morphology is controlled by tectonic process and also by mud diapiers. When a geomorphologist see this canyon channel, they say, aha, this shows the young stage of a river system. You see all these meanders, but they are wrong. These meanders are actually created by the mud diapiers. These are the temporal structure of a vertical temporal change of vertical structures of salinity, temperature, and light transmission over a diurnal tidal cycle. And you can see that when during the flood in the canyon, colder and more saline water enters canyon from below. During the ebb in the canyon, warmer and less saline water pushes cold water out of the canyon from above. And at the top, you also see in the salinity data, you see a thin layer of the Gaoping River plume. The bottom panel is the light transmission. And you see 4 high value areas, that means high suspension areas, is coinciding with the maximum flood and ebb currents in the canyon. And usually there is a nephaloid layer near the canyon floor, whose thickness is modulated by tide and also by any flood events of the Gaoping River. The tidal control really also showed the the current structure along the canyon also showed the tide control. And with tidal phases, with the different tidal phases, you see the switch of current directions, but there's always a two-layered structure in the canyon, in the flow field. Within the canyon, the depth average, the turbulence kinetic energy dissipation rate, and the depth average, the eddy diffusivity are more than 2 orders of magnitude greater than typical values in the open ocean, and much greater than those found in the Monterey Canyon. So this also makes the canyon very unusual. Now, if we look at the density structures and the suspended sediment concentration patterns, they are closely coupled. Here, these are snapshots of the isopycnal surfaces and suspended sediment concentration at the different tidal phases. You actually see 3 types of nephloid layers. There is surface nephloid layers, and intermediate nephloid layers, and the benthic nephloid layers. Or if you will, you can call them hypopycnal plume, mesopycnal plume, and hyperpycnal plume. And these are the plumes that mainly follows the hyperpycnal surfaces. But there are other situations that the suspended sediment concentration, the localized suspended sediment concentrations do not follow the isopycnal surfaces. They were caused by the shoaling internal waves. When the internal waves hit the canyon floor, they break and the energy gets dissipated and to cause suspended sediment concentration to increase. So the interior of the submarine canyon is by no means a quiescent environment. There's constantly motions driven by baroclinic, barotropic tides, and by internal waves. And occasionally they are gravity-driven flows or turbidity currents. It is this environment into which the river sediment comes. There's also a diversity of the sediment sources for this sediment. The hypopycnal plume disperses fine-grained terrigenous sediment, and the hyperpycnal plume delivers coarser sediment into the canyon floor. And on the shelf, there are particles, biogenic particles related to primary production. Also, there are benthic and the planktonic forames, and also the resuspended rework sediment from the shelf floor. All this sediment fall through the canyon interior. In the process, they go through physical and geochemical transformation. And when they hit the canyon floor, that's not the end of the story. Within the benthic nephloid layer, they're constantly being eroded or suspended and deposited by gravity-driven processes. There is one example. This is a short gravity core taken from the floor of the canyon. You see the grain size composition of clay, silt, and sand. Over here, there's a large sand bed. And corresponding to this is reduced TOC content. And also this is the axis lead 210 profile. Obviously, this is some kind of disturbance or event that interrupted the normal sedimentation pattern as indicated by the different truncated shape of the axis lead 210 profile. And that indicates that this is some kind of disturbance. It could be a turbidite deposit or a hyperpycnite deposit. This is just to show that inside the canyon, it is a very common feature in the sediment cores that we got. Okay. Now, next thing we're going to move on to a very important tool that we use to study sediment dynamics. That is sediment trap mooring. Here, the moorings, the sediment trap that we use consists of a cone, which is it's like a funnel. And underneath, there is a tubing with a core liner inside. Near the opening of the cone, there is a gizmo that is the timer or intervalometer. This thing dispenses Teflon discs at the predetermined intervals. So when the trap is in the water collecting sediment, and then the intervalometer would dispense a timer disc. As the collection continues, the next disc, and then more accumulation, the next disc. The intervals of discs are predetermined. Okay, so when you go to retrieve the sediment trap, voila, you have a sediment core suspended in the water with embedded time markers without erosional gaps. This is a dream of every sedimentologist. Now, we got this through the collaboration with J.P. Xu when he was working at USGS. And he sent us a whole set of the sediment trap completed with the strong bag and the baffle. So we made the duplicates of the system. And so in our research, we used the duplicates. But we encountered a problem. The original honeycomb-shaped baffle is patented in the US. We couldn't buy it. So then we used Taiwanese ingenuity. We used the straws of bubble tea to make the baffle, which worked just as good as the original design. And in our first sea trial for deployment retrieval, Jinping came over to Taiwan just to make sure that we did things right. Okay, that's him. So now I'm going to share with you two studies we did using this, I think, a very, very powerful tool. The first study is under normal conditions. We deployed a sediment trap mooring at this location. It is configured with other instruments, but the focus is on the data that the sediment trap collected. When we retrieved, this deployment was for 2 months, was from January to March in 2008. And during this 2-month deployment, the sediment trap collected 62 centimeters of material. And after we got back to the lab, we slice the material at 1 centimeter intervals. And with the samples, we analyze the grain size. So, and we plot the down core distribution of the coarse and fine fractions. Also, the mean grain size for each slice. And for the next 3 panels, we plot the percent clay versus water content, TOC and TM, just to show that the clay is the primary vehicle to carry biogeochemical signals. The next panel is the mass flux or accumulation rate. The diamonds are where the timer discs are located in the trap. So, and the in-to-each timer is the fixed duration. And the max flux was calculated based on the dry weight of each slice. So please notice the number. Okay, the maximum max flux is almost 300 grams per meter per square meters per day. That is very high in the world. And the higher values of mass flux coincide with spring tide. So in this 2 months, we encountered 5 spring and neap tide cycles. Spring tide, time of spring tide is indicated by these red arrows. Okay, how does that affect our sediment? We see that during the spring tide, we collect the higher amount of coarser material. That makes the mean grain size larger. However, it is the fine fraction, the clay, that carries the biogeochemical signal. That's why having a sediment trap like this will give you a lot more information by using other type of collecting tools. Now, the fine fraction is equivalent to the hemipelagic mud that we see on the canyon floor and on the slope, on the Gaoping slope outside the canyon. Our teammate Jian, who also did the radioisotope analysis of the samples for us, and this is the X-lead-210 profile and X is thorium-234. And if you, the ratio of the two shows a almost straight log curve. This, according to Qian, is a typical textbook case of steady sedimentation that you would see in a sediment core. Now, we have flow measurements. We have sediment, suspended sediment concentration in terms of the echo intensity. So, and this, so we multiply them. That's the transport, and this is a progressive plot of the transport during this 2-month period. And you see the individual tidal cycles, and the net direction is up canyon. And that's as a result of a tidal regime. We'll come back to that. Okay. Now, the next study is for similar observations, but under hyperpycnal conditions. So in the same year, from July to September, also for 2 months, we deployed another sediment trap mooring with a long ranger ADCP at the same location. And this line is drawn to scale of the length of the mooring. So the top of the mooring came up to the rim of the submarine canyon. On the mooring was also configured with 18 thermometers. There is a acoustic current meter and the sediment trap. Very simple configuration. Now, during this 2 months, 4 typhoons came by. 2 made landfall on Taiwan, and 2 just went into the South China Sea. The signature typhoon, as indicated by the atmospheric pressure record, the precipitation from 2 stations near the river mouth. And the next panel is the daily river discharge and suspended sediment concentration. The blue line is interpolated, that's after doing the rating curve, and the red circles are the instantaneous measurements. The next panel is the wave measured on the shelf, wave height and wave period. And these are just very common data you would expect to see during typhoon. Now, I'm going to show you measurements on the mooring from the acoustic current meter. Okay, in this panel, the yellow line is the acoustic backscatter or echo intensity, which is indication of the suspended sediment concentration in the water. The red sticks are the stick diagram of the flow measured by the current meter. And here you see a abrupt rise of the acoustic signal of the suspended sediment concentration, and with a very strong current marked in red. And also coinciding with this occasion, we see warm water coming up from below. This panel is temperature anomaly, okay, from all the 18 thermometers. So in order to ascertain if this data is correct, we took a closer look at the 24-hour period surrounding this event. On the top panel is the flow field, the observed flow, that's blue, and we decompose that into a tidal and a non-tidal component. So we can see that this large anomalous flow is actually non-tidal. Okay. Now, the next panel is the acoustic signals. I'm sorry, the acoustic backscatter signal. The suspended sediment representing suspended sediment concentration. So, as the suspended sediment concentration rose, when the flow, down canyon flow increased, a warm water plume came up. Okay, and then when the flow subsided during the after the waning, and there is a after the waxing, there is a waning period that the water subsided, and measured by the upper looking long range ADCP. This is the vertical structure of non-tidal flows, and the red color indicates seaward. So you see that the warm water plume coinciding with the seaward flow. Then the next plume came up. What does this mean? What does this mean? If we compare with the schematic plot of the structure of a turbidity current. It consists of a head, a nose, and also there is billows at the top of the flow due to the Kelvin-Helmholtz instability. And this billows, in fact, is the warm water plume that we saw. Now, this extremely high down canyon velocity, which is over 3 knots, is actually the time when the first turbidity current went through the mooring, went by the mooring. So we know that, yes, physically, we capture the warm water that a turbidity current passes the mooring. Now, our sediment trap data also corroborate with our physical measurements. Because of high mass flux, during that time, the sediment not only filled the tube, but overflowed into the cone above and buried the lower part of the timer. So when we analyzed the samples, we only discovered 3 timer disks, number 1, 2, and 3. All the others were stuck at the opening because the timer was buried. So we had the time for these 2, for these 3 timer disks. And here, inside the sample, we found an interface that has a strong color, contrasting color. And we determined that interface coinciding with the time when the turbidity current came through. And the head of turbidity current carried a lot of terrestrial material, indicated by high amount of total carbon, TOC and TIC, and also high CN ratio. Now, so we have 5 day points, and the period between them we can use to calculate the mass flux. Now notice the unit is now the kilogram per meter square per day. So actually the maximum is 180 kilograms per meter per day. And that is astronomically high, carried by that we measured. So what did we measure? Okay. Compared to Mulder said that if the river flow has waxing and waning stages, and if the flow exceeds the threshold, if the suspended sediment concentration carried by the river exceeds the threshold of 40 grams per liter, and hyperpycnal plume would occur at the river mouth, and then would form deposit on the seafloor consisting of a inverse graded bedding superimposed by a graded bedding, coinciding with the waxing and waning stages in the river. So when we look at our sediment trap data, we did see 2 episodes of waxing waning events. And this particular, the first event, this coincides with the strong terrestrial signal in the sediment. We examined the sediment at in this slides. We see that it consists of a large amount of plant material, of leaves and roots and twigs, with other classic sediment. So that's an indication of terrestrial source exported by the typhoon. Now, the lower part in the sediment trap has high percentage of sand. That is equivalent to sandy turbidite if all this material would have been deposited on the canyon floor. And above that is equivalent to hemipelagic mud. You see actually three episodes that would be equivalent to the spring tide. So radioisotope traces also reflect the very highly disturbed typhoon floods, and that the created by the hyperpycnal regime. And then the system went back to the normal tidal regime. You would see the steady sedimentation pattern. When we plot the progressive vectors, we see that originally before the first typhoon hit, I was landward up canyon directed transport that reflects the tidal regime. Now, when the first typhoon hit, the transport switched to seaward. And then through the next two typhoons, there was a transitional period. Then eventually the tidal regime assumed. There was another sort of super typhoon events that we recorded. This was Typhoon Fanapi. We're very fortunate for this typhoon because before the typhoon came, we already had a ship time scheduled to deploy 2 sediment trap moorings over here. And so 6 days after the peak river flow, we deployed our moorings, and the Fanapi signal is over here. So these were also simple moorings configured with a sediment trap and a upper looking ADCP, and XR420 is a CTD. And this mooring, KP3, is configured with a downward looking ADCP and a CTD. So the CTD and ADCP would give us 2 levels of temperature record, and the same here. And the XR420 would give us a salinity, and then we can compare. Okay. We discovered that the original US GS type of sediment trap, and they call it the Anderson type, and we call it non-sequential as compared to the rotary type of collecting cups we used before. Now the original design for the timer, the intervalometer, the highest interval is 1 disk per day. And if you want to capture episodic events, this is just not adequate. So instead, we replaced the disk dispenser with a acoustic altimeter. So we send down sound waves at higher frequencies from the distance between the hydrophone and the surface sediment. We could infer the accumulation. That would give us better time resolution when we especially we want to capture episodic events. And also for this study, we did not take water samples to analyze suspended sediment concentration. So we use the sediment captured in a sediment trap, assuming that they all came from the water column above. So we use the captured sediment to make concoctions of different mixtures of different suspended sediment concentration, and did a verification on the measured turbidity, and we got good result. So we converted the turbidity values to suspended sediment concentration values in terms of kilograms per cubic meter. And these are the salinity temperature data. We see that throughout the deployment, the salinity slowly rose to normal level, because what we did was we captured the wake of a hyperpycnal event triggered by Typhoon Fate. Okay, and the temperature also it was warmer, then it became colder, and so how did we determine this time? Okay, so we put these three variables, temperature, turbidity, and salinity, through the EOF analysis. That is the first mode. It shows two groupings. Temperature and the turbidity are grouped in the negative value by the negative values, and then the other the salinity is in the opposite group. And the fact that the salinity and temperature are on the opposite side, that indicates river plume signals, because usually you have high temperature and low salinity. And that's what happens in the canyon. And this curve is the eigenweightings of this mode, which represents the temporal pattern of this grouping. And this curve has a zero crossing. This crossing is the demarcation between the hyperpycnal and the tidal regimes. So now we can look at from with that this new revelation of time. If we look at that in the hyperpycnal regime, the temperature, the two temperature records on each mooring actually show the reversal. This means that the temperature in the lower water, in the deeper depth, was actually warmer than the temperature above. And it's because of the hyperpycnal flow. So this happens for both moorings, and we see in the hyperpycnal regime, the non-tidal part of the flow was always seaward, and in the tidal regime, the tide took control. So you see stronger tidal signals. Now, the next thing is to deal with the captured suspended sediment. Turn out that there is something that we need to overcome. We believe that this is a bottleneck effect. The acoustic telemeter, the signals was blocked by this opening. So when the trap first came in, we had two readings, and then the reading showed that the accumulation was at this opening. So it stayed for a while until the collected sediment overflowed into the cone. Then we began to measure the real accumulation. So we used the empirical mode decomposition to get a linear trend of this. And then we made a spline fit between the origin 0 point and the end of this line. So that forms the so-called the smooth observed accumulation. Now, is that real? So we use the simple Rawls equation based on the law of the wall, and we came up with this theoretical accumulation. Okay, so we decided that the difference is actually caused by the trap efficiency, that we only trapped 43% of the suspended sediment in the water column, in the water above the opening of the sediment trap. So having the advantage of a timer is really, really good, because now we look at the mass flux. We see that it gradually decreases. So originally, near the during the wake, in the beginning, the mass flux was higher than 50 kilograms per meter square per day, and gradually reduces to about a non-typhoon spring tide level, which is a few hundred grams per meter per day. And this tells us that the duration of a hyperpycnal event is on the scale of days. In our previous study, we measured the hyperpycnal event on the scale of 14, 15 hours. Now we extended the scale to days. Now we're going to look at the substrate signature of the dual sediment pattern along the canyon conduit. I'm going to show you three long cores. The first one is near the river mouth, and you see very thick sandy deposit mixed in with hemipelagic mud. Okay, because this core is the closest to the river source, and then farther away we see dark bands. These are actually turbidite layers, okay, intermingled with hemipelagic mud. And if you examine each turbidite layer closely, you will see a sharp boundary, erosional boundary, and you will see the graded texture finding upward. Then gradually it merges with the background hemipelagic mud, and the boundary is indistinguishable with the naked eye. That's why we need to use X-ray radiograph. Now you can see the boundary of the upper boundary of each turbidite very clearly. As we move farther down from the river mouth, in this core, the turbidite layers are faint and thin and of finer grain sizes. So this is spatial difference in the in the occurrence of in the thickness and the grain size composition of turbidites really fits a river-fed canyon scenario. Okay, so based on our observations, there are close couplings among the physical processes, net sediment transport, dynamics of settling particles, and substrate signatures. So the theme is tidal versus hyperpycnal regimes. Now, the last subject is the new is old. Okay, why do I say that? Now, this has to do with the internal sinks. This was taken at the junction of a tributary that flows into the Gaoping River, beginning from 2005 and 2012. Over the 7 years, you see the development of a terrace at the junction. Okay, this is a very common thing in rivers in Taiwan. Whenever there's a tributary flowing to a trunk river, you always see terraces. And these terraces are actually temporary sinks because they are subject to catastrophic flood events. And on the time scale of 100 to 1,000 over 10,000 years. Why do I know that? Right after the super typhoon Morakot, I think 6 weeks after that, we took a core right here. Okay. By the way, this is the plume right after the typhoon. And the orange streaks are actually a driftwood. Okay, that's another issue. Now, this is the photo of the core, and the red line is the mean grain size of the core. You see over here, there's a thick, there is a coarse deposit, okay, corresponding to high TOC and high CN. This is because there's a turbidite layer, turbidite bed here. Now, we took 3 samples to measure the AMS, use the AMS carbon 14 dating to measure the date. And we found that the youngest is 8,000 years within the turbidite. And then there's about 10,000 years old, 12,000 years old. So these are the sediment that just came out of the river, and it's already old. Now, that was from a sediment core. Now, going back to this study that I just showed you, sediment captured by the sediment trap, okay? And we measured we dated 3 samples. Their age is between 6 to 8,000 years old. These are suspended sediment that are aged. So this is, I think, a very, very interesting, because that shows that this reflects the effect of internal sink that delayed the export of material, or if you will, the age could be, you could say, is residence time. Now, this internal sink not only exists in the watershed, but also in the submarine canyon. We see slumping along the canyon frequently. Okay. And another short core we took from the canyon, okay, and we enlarged the first 40 centimeters. The green band shows that this coarse part, the coarse fraction in the core is actually contributed by fresh terrestrial material, in showing a high TOC and relatively high excess lead 210. And the coarse material down below was actually from material inside the submarine canyon, as indicated by low TOC, low excess lead 210, low water content. And this bed also disrupt a otherwise would be a more well-behaved profile of excess lead 210, TOC, and the water content. So again, this shows that perhaps this is caused by this material was sourced from an internal sink inside the canyon. So now from a observational standpoint of view, if you stand here, if a mooring stand here, if a turbidity current originated from hyperpycnal plume, you would measure warm water as we did in our studies. But if a turbidity current is triggered by landslide inside the canyon, then you would not encounter warm water. But if you have a sediment trap, if you look at the sediment that both turbidity currents carry, using the correct proxies, you can tell the sediment carried by these two turbidity currents are sourced from different regions. Okay. Now, just to summarize, the Gaoping River canyon dispersal system consists of a high-yield river catchment that is dynamic in its fluvial and sedimentary behavior, and a submarine canyon whose sediment dynamics are controlled by tidal oscillations under normal conditions in which the net sediment transport is up canyon, and by sediment gravity flows under typhoon-induced hyperpycnal conditions in which the net sediment transport is down canyon. There are two modes of sedimentation patterns in the canyon. The hemipelagic mud is formed in the tidal regime, and hyperpycnal turbidity currents form coarse-grained to fine-grained turbidite sequences. There are close couplings among the physical processes, dynamics of the saline particles, and substrate circuitures in the canyon. The newly exported carbon during extreme event could be aged carbon in a highly disturbed watershed, such as Gaoping River. Thank you. I'll stop here.
Oh, great, James! Such a comprehensive and great talks. So you show how a river flow all the way from 4,000 meters all the way to more than 2,000, 3,000 meters in deep ocean. So and also you talk about the tide driven, the hyperpycnal driven, the even compare the landslide. I mean that's a great sediment carbon and it's wonderful. So okay, now we open to the audience. If you have any question, just go ahead, unmute yourself and ask Professor James Liu. And or if you like, you can type your question. For the YouTube channel, if you like, you can type a question there, or you can come here on the Zoom interacting with James directly. Go ahead, any questions?
Well, I don't bite.
Oh, okay. Yeah, very informative talk. Thanks, James. So my question, yeah, good to you have a summarized slide from the process to product. You show I forget which one. You show you have a yeah, maybe this one, yeah. Right. So you mentioned before you have a depositional sequence in the middle from a tube. You got the information about the waxing and the just the last slide 40 yeah, this one. At the middle column you have a waxing and the wearing signal at the bottom, yeah. And if we look to the core, the short core, we only have a half cycle. We only have a firing upward, low proceeding upward. So that means some signal from the tube going to yeah, go away from the real depositional sequence. So what happened? And another thing, you mentioned, yeah, usually the hyperpicaleo event occur very only loss of frequently, but the internal tide very strong here. So hyperpicaleo deposition going to be reworked by internal tide. So finally, what kind of signal going to be preserved in the canyon bottom? So that's my question.
Okay, thanks for the question. I think the key word is preservation, because how can you preserve? You know, it's constantly the canyon substrate is constantly being disturbed. So preservation is really a problem. And I think Mulder's model and the hyperpycnal sequences can only be observed if you use a sediment trap like I use, because there's no erosional gap. If you look at the real thing on the sea floor, usually this is a sharp boundary. It might be a erosional boundary, you know, and so we don't know. We know that this part of hyperpycnite is preserved, but we don't know what is not preserved. So, yeah, there's a lot of mysteries in this. Yeah.
Okay.
Can we find some tidal deposition signature here?
Deposition. Okay. Going back here.
Internal tidal so strong there. Impossible, right?
Say it again. What?
I mean, yeah, except hyperpycaleo deposition, and we find some tidal signal in the deposition.
Hyperpycnal deposition?
No, I mean, can we find tidal?
Tidal.
Some tidal.
Okay.
Because you mentioned internal tidal is very strong. Yeah. And can it rework the sediment there, I think, yeah.
Well, again, if they don't get preserved, you don't see it in the seafloor sedimentary record. So
okay.
Yeah.
Okay. Hey, James, you know,
Yes.
Taiwan, you know, every year there's you know, at least a couple typhoon made landfall and it's a storm, you know, in this area. So you show also the evidence in the canyon wall collapse, like a landslide, that generate some kind of turbidity current. So did you observe in the canyon head close to the shore, is that canyon head is become deeper or become wider? Is any, I know maybe we only have a decade to observation, but any evidence show that canyon, you know, is become a little bit deeper, a little bit wider? I mean, this is the first question. Yeah,
that's a good question. Your former advisor, John Milliman, asked me a similar question.
Oh,
okay, if the tidal transport is up canyon, then the canyon is going to be filled up. But then I think when the next hyperpycnal event comes, it reset, it just flush out all the previous accumulation out to sea. Yeah.
There could be, you know, I don't know, could be deeper and deeper, you know, because up near the shore, that could just serve like a channel, like a conduit, sediment just bypass. And this is second question: how deep, how far those hyperpycnal or turbidity signal sediment can send it to the deep sea? How deep they go?
Actually, Pete Tolling would believe that it's a long run out. We use the submarine cable breakage information to estimate. Lionel Carter and Rachel Gabby have done that. Yeah. So actually, Pete Tolling want to conduct a study that trace the long run out all the way to Manila Trench.
Oh, but so far you don't know exactly how far they go.
No, we don't.
Well, we should do it. I mean, if Taiwan don't do it, mainland China should do it.
Actually, you know, Zhifei Liu have done something on the downstream part of the canyon. And so, yeah. But the key is really at this opening, river fed. So if the turbidity current is triggered by a river hyperpycnal plume, then to start at the river end, at the canyon head is important.
Yeah. So very interesting how far, because if you look at, I think Peter Tolling also in the audience here. So if you look at the Ganges Brahmaputra in Bay of Bengal, and it's possible the turbidity or hyperpycnal through the canyon can reach very, very far, much, much deeper than we initially thought. But in this system, we want to know how much of the Gaoping River from sediment from Taiwan can contribute to the northern South China Sea shelf, and directly or indirectly. This is some kind of question many Chinese colleagues, also international community are very interested.
Yeah, certainly. We hope Peter Tolling would come to Taiwan and then finish what he proposed.
Interesting. Very good. Okay, anybody else a question? Who is this Huawei P10? Do you have a question?
Huawei.
James.
It's me.
Hi.
My name is Zhou Liangyong.
Oh, okay.
Hi.
It's a very interesting talk. I have some question, but please let me tell Professor in Chinese.
Okay.
我听到这个 OK，
我听到这个 no problem, go ahead.
刘教授这个讲座吧，非常有启发。因为最近吧，我一直在看这方面的文章嘛，就有一些问题吧，就想这个请教一下刘教授。刚才那个我刚才听了那个，就是刘金普老师也说了，就是我们这个浊流吧，就是说它从这个河口出来以后，达到多大的深度，它能形成可维持的这个就是autosustain的这个可维持的这个浊流嘛？因为从这个叫这个一中流形成过程来说，不是它经过一定深度才能形成这种浊流吗？我就这个深度这方面。
OK，
能听得明白吗？因为我为什么提这么一个问题呢？因为我们黄河三角洲吧，也是研究一中流的一个地方嘛。但黄河三角洲的问题呢，是它这个海盆吧太浅了，它到这个就是叫 bottom set 吧，只有15米。
yes。
然后高平这个地方呢，它要深得多，是吧？
是。
所以这个在那个 Lamb 和 Mohig 在这个 Geology 发表一个论文，他就用一个模型吧，就是预测，就是如果是深度不够的话，它可能就是说，在没形成浊流，这个一中的水体吧，在没有形成浊流的时候，可维持浊流的时候，就已经消散了。就是我所以对这个深度也很感兴趣。
Okay.
Certainly, I think it's not the depth. I think it's the slope. If you are familiar with the downrights work, and the slope is very important because turbidity current, by definition, is density driven. So, in order for this engine to work, you need to have a high concentration, and to begin with. And you need to have a gradient. So I think there is a misnomer if you think high concentration water body would form turbidity current might not be the case because it needs to be density driven. Okay, you need to have a density, high density difference between your turbid water and ambient water that creates this density gradient, and you have the slope that sets the stage for this body of water to flow down slope. Once it's flowing, according to Octavia Scoria's flume work, and there are 3 types of, this turbidity could remain constant speed or it could accelerate to decelerate. It all depends. Yeah, depends on the situation. If your turbidity current is picking up sediment from the seafloor, and that would accelerate. If you lose sediment and you form turbidites, then the flow would stop. Then if you reach a balance, then the flow could continue, have long run out.
还有一个问题啊，就是说我注意到吧，你没有用那个 hyperpicnite 这个词，而用了 turbidites， 好像是，就是说，因为现在关于这个 hyperpicnite 吧，有很多争论，我想你肯定也注意到了，特别是我们搞这个石油地质学的这些专家吧，对这个问题特别感兴趣，他们就是也想从我们这个海洋观测的角度吧，去这个得到一些证据来证实这个可以从沉积物的，就是winding 啊，就是 waxing 啊这个序列，或者说是它这个一些纹层来判定这个属于一种流。最新的一种模式呢，它一是这个方面的证据，现在最新的模式呢，它想从流变的角度吧，这个来识别。我听着你这个角度吧，我发现从流变角度吧，它也存在这个问题，就是你对这个问题有什么看法
？Actually, the terminology can be very confusing because there are many disciplines that all study the same thing: sedimentology, modelers, and observational geologists, and people who do flume studies. And in terms of turbidites, hyperpicnite, all depends on, by name, turbidites are formed by turbidity currents, which is a Newtonian flow of low concentration. Hyperpicnite, I think it's very similar. It's because the turbidity current was triggered by hyperpicnal flow. I think it I think it's the same thing. But geologists and sedimentologists, they have a different criteria for that. So actually, in my paper, I did mention hyperpicnite and turbidite because actually, when you look at a soft core, as I show, it's hard to decide that which mechanism actually formed this deposit. So, yeah, I have no answer to that question.
Okay, good.
Okay. Thank you.
Yeah, James, so anybody else, if any question? And James, if somebody, if you try to write a review paper, let's say the role of the canyon transported terrestrial carbon to the deep sea. This is the title of a review paper. If they try to put Gaoping definitely is an important candidate. So how much terrestrial carbon Gaoping every year we estimate transport to the sea?
Well,
you have a number?
I think Shu Jigao, Cui Gao is a better person. He was my one of the collaborators. He studied carbon, and also Niels Hovius and his previous postdoc, Robert Sparks. They are the carbon people, so I think it's better for them to answer.
Sure.
Yeah.
Okay. Yeah, because this has become also interesting. Like Christoph a couple weeks ago, his presentation about the Congo River, and that's become interesting. But anyway, if no any other question, I think now is already 10:20, so I think we can stop here. But once again, this talk is available online, and if you can rewatch this talk. And also, again, this Friday we have a talk given by Sarah, and talk about Amazon POC and from the source to sink. So, okay, James, thank you very much, and many our Chinese colleague. So it's very interesting. Okay.
OK，谢谢各位 ，Thank you，Thank you for hosting。
Okay.
Bye。
再见。